Okay, thank you once again for coming to the AI seminar. It's my great pleasure to introduce Ashkan Panahi. He is currently at North Carolina State University, and he's a postdoc, or I think your title is research associate, right?
Research associate.
Yeah, with the National Research Council, and he works on really interesting, kind of diverse, cross-cutting stuff. Theory for machine learning optimization, also algorithms and tools, and actually applies these. And you don't just sit in theory, applies these to multimodally to both vision and NLP video. He worked on NLP for the previous postdoc at Chalmers University of Technology in Sweden, which is also where he got his PhD. And further ado, that's what we will.
Thanks so much, Dr. May. I also need to thank you for letting me here and giving the talk. I also thank you for being here and listening to this talk. And I hope that you enjoy it. So about the title of the talk, so this is the story. I picked two topics which are even more theory because I thought that these topics will be more interesting for a broader group of people here. And so once I picked the projects, it was really difficult for me to come up with a title. After thinking a little bit, I realized that basically what I've been doing is kind of related to geometric systems. Yeah, sure. So basically, I'm going to introduce two different projects from my past research, and so we'll see. They are connected also to each other. But before that, let me start by giving a little bit of background from myself. Dr. May already me. So I'm going a little bit back. I was born in Tehran, Iran, and I received my bachelor's degree in Tehran from the Iran University of Science and Technology. And then I moved to Sweden. I received my master's degree in communication engineering with a specialization in systems theory and information theory. And then I joined the signal processing group at Chalmers University, where I got my PhD degree. And then I moved to the computer science department in Chalmers, where I did more machine learning stuff, mainly related to NLP, but there we started to do larger scale optimizations until I received an award for research in the US by National Research Council, and I moved to North Carolina, where now I'm doing my research. So this is a little bit of my background in general, and you have the pictures of different universities. They're pretty diverse shape. Okay, so also I have done different projects. So I have a short list of the major ones. I've done also smaller ones. I don't have time to go through all of them, and so I'm just going to talk a little bit about each of them. So my PhD was in sparse modeling in general. We applied it for certain problems in estimation and detection. It was related to sensor data. But certainly I learned a lot of different things about optimization in my PhD. I've done something about the theory of compressed sensing. There we use statistical tools for large scale analysis. We did a universal analysis. Basically, this is the part that I in Caltech visiting at the university. And then mainly in my postdocs, I did, my research was about a larger scale optimization techniques applied to machine learning. And this is what I'm going to mainly talk about today. So since I came here, we've done more things related to computer vision and image processing. One theme was subspace clustering by non-convex optimization. This is a very interesting area. Unfortunately, I don't have time to talk about it. In the next slide, you will see something cool about it. Deep dictionary learning is something that looked at in the past year. It's a combination of dictionary learning, which is basically sparse coding, and deep learning. There is a literature on that, so we somehow contributed both theoretically and algorithmically to this area. And something that definitely I would like to talk about, but I don't have time, unfortunately, is this network modeling and community detection. I learned a lot of cool stuff in the past year about computer detection. I suppose that you are familiar with optimization-based techniques, convex optimization, nuclear NOR. But there are other things that probably I talk in the last slide if I have time. All right, so just to show you a cool project that we did and finished this year. This is a video this is a project where we detect the motion, the moving parts in a video. So the top one is the original image. In the bottom, you see two things. The left one is actually our method. The right one is another older method. You see, this is difficult because the shadows and lighting can be considered as moving parts. So it's not a trivial problem. It's actually a very difficult problem to solve. And we used non-convex optimization based on subspace clustering that gives us a very good performance.
What's the goal here?
To detect the moving, to decompose the image into two parts. One part is the background, which is constant, and a moving part. Yeah, but this is not what I'm going to, yeah, sure.
Yeah, when you say moving part, you mean humans, right? No, not shadows.
Not shadows, humans. These are the parts, mathematically speaking, these are going to be classified by subspaces. And so what we mean by moving part is the more dynamic subspaces in the composition of the image. Yeah, so this is something that we've done. I will be happy to talk about it afterwards, but this is not really the topic of the talk.
All right.
Quick clarification. You say humans, but it doesn't have to be any movie.
No,
yes, exactly.
There is another movie, I don't have it unfortunately here, with cars. This
Cars.
is the MIT data center. That is more popular for background program separation.
Like some all background subtraction, but you do it with statistical learning or.
Exactly. But now these setups are more challenging because the difference between background and foreground is not clear.
Yes.
For borderline cases like trees where leaves might move it.
Exactly. You can also capture dynamical background. That is something that we also consider. And also shapes, changing in shape, something like trees. And when you have a pattern change data, that you can capture the subspace. Okay, I didn't know that you would be interested in this talk, but I would prepare something related to this. Okay, so I hope that you enjoyed this one as well. What I'm going to talk about, so this is, as I said, we have two parts for this talk. One part is the major part. I've already lost some time, but I try to talk fast and cover this. This is the main part. It's about variance reduction optimization techniques for machine learning. I suppose that many of you know about this area because whoever who works with deep learning have done something with incremental optimization. So probably you know these mini batch processes. So mini batch means stochastic gradient, incremental stochastic gradient descent technique. But we are going through it, and I try to cover the basics very fast and talk about the part that we have. Okay, so generally in this kind of optimization, you will have many terms in your objective function. If you're doing statistical learning, usually these terms come from different data points because you usually do a likelihood-based thing, and then each term appears as a log likelihood. It can be something different, but it's very popular that at the end of the situation that you have many terms relating to different data points that you have observed. Okay, so in this case, then if you want to solve this optimization with gradient descent, you'll have a problem. Calculating the gradient is very expensive. You have to calculate it, but then if you're going to use this gradient, you have to be careful that you use it in the best possible way. So one solution is that you do something called incremental. So you take incremental steps. You create simpler steps so that effectively you're calculating the gradient, but meanwhile you're updating your data a lot more than just gradients. Okay, a very famous example is the stochastic gradient descent, where the incremental step is only the gradient of one of the terms. And then you go through the terms either in a schedule or by randomly picking the term. Okay, this is really good. That is what modern machine learning for larger scale optimization is based on. The good thing with it is that with the same amount of computation, you usually get a faster convergence. theoretically there is no gain per se, but what you really gain is very practical. It can be reduce your computation from days to hours. But usually it's just theoretically it appears as constant. So equivalent, you can say that you are avoiding memory issues. So if you have ever implemented convolution on neural networks, you know that the state space is really high, the feature space is big. So when you're calculating back propagation, then you have to keep all these features for calculating the gradient. That means that for calculating one gradient, you need a lot of memory. So if you want to do everything in a big batch mode, it's usually impossible. That's why we use big batch processing. So this is another way to put the same thing. And also, one thing that is less noticed usually is that it also helps with choosing the step size. If you have a gradient descent, you have to be really careful with the step size, but because the convergence of the stochastic gradient is in a probabilistic sense, you can go wrong sometimes. So you don't need to do a very careful job when you're doing the that is why this thing has become very popular, but of course there are very clear consequences with using this thing. One is that you don't really get convergence. So people use it, and if you look at the curves, for example, in deep learning, you see that you have a noisy thing going up and down, and then it converges. But still, when it converges, you see that the noise is there. From optimization point of view, that means that you haven't converged yet. But for practical purposes, it's just fine. So one thing is that you don't converge, and you can simply see it from the equations that we have. So let's say that you could converge, then you would be at this point x star. At x star, the gradient vanishes. That means that the sum of the gradients would be 0, but the individual gradients are not 0. So if you take a step, then that means that you're going somewhere else, that the gradient is not 0. So basically, you get something that probabilistically can be called a variance. So if you randomly select this gradient, around this optimal point, you get a variance. Go around. So that is a problem. So practically, you need to decrease the size of your step in order to decrease this variance. Also, it's clear that the gradient descent works for differentiable functions where you have gradient. If you don't have gradient, you cannot apply a gradient descent, of course. But I mean, you know that in many cases you can use gradient descent, although the gradient doesn't exist everywhere. Also, there is no constraint in this optimization. And in the next slides, I'm going to quickly go through all these 3 problems and show you some solutions from the literature. So the non-smooth case is simple. So it's now, I guess it's very well established that for the non-smooth optimization, you will have something called the proximal operator that replaces the gradient. It might be difficult to calculate, but in case that the optimization is simple, then you can have a cheap iteration that replaces gradient. And this is called the proximal operator. I assume that you know a little bit about it. Otherwise, just think about it as an operator that if you apply recursively, you will converge the solution. Okay, so now the idea is that instead of applying gradient, you can apply proximal operator. Okay? And you do the same. You just randomly pick one of the indices, and instead of applying gradient, you apply proximal. Okay, now there's a theory for this. It's a very well-known theory, kind of old now. I guess it should be around 8 years. So if you, I'm missing some new information. If you have the correct decrease in the step size, then Bertzekals have proven that this scheme is going to converge with probability 1, which is a strong sense of convergence. Now, what we proved is that if you select a specific type of step size, then you also have a guaranteed rate of convergence, which is as close as you can get to 1 over t. 1 over t here is kind of an upper bound for your convergence. The reason is that 1 over t is the convergence rate of gradient, so you cannot do better than gradient with the stochastic gradient. So we proved this, published it last year. Okay, so now this is the first issue with non-smooth. The second issue is that, which is more important, is that is the problem of vanishing step size. The problem is that in practice, you cannot use this theory to shape your step size. Usually people use adaptive type of step sizes. This is something a little bit different. But anyway, there's no established way to do to decrease the step size. So it's always desirable to use a fixed step size. You can actually do that with a technique called vanishing rate. So the idea is that you replace your incremental step with something more sophisticated, so that once you reach the optimal point, this gradient, this variance that we talked about is going to vanish. One idea is that you make a table of different gradients. So for each term, you will have one entry in this table, keeping the last gradient that you have calculated. So instead of throwing away the gradients, you put them in a table, and then you use it. A very simple idea is that you just add them and use it as an estimate of the gradient. This is called the SAG algorithm. Another idea, which is a little bit modified, gives you a smarter way to combine these elements. And the specific reason for this is that it will reduce the bias. So you will get unbiased estimates of the gradient. And theoretically, you can see that helps with convergence. Okay, so what about the non-smooth extension? So we talked about non-smooth and then about the vanishing gradient. There is actually a non-smooth version of the Saga algorithm, which is actually proposed much later than the original Saga algorithm. So the idea is again to mix your table, the elements from your table in each iteration, but now you apply the proximal operator. Okay, and now you don't have the definition of gradient to keep in your table. What you keep in your table is something called the subgradient. I suppose some of you are familiar with this idea. And the nice thing with proximal operators is that they give you a subgradient. So that is the last line in this equation. So instead of keeping the gradients in your table, you're keeping subgradients given by the proximal operator. And then you go on continuously. So with this, you get a convergence rate. This is proved by Fazio. You get 1/t convergence by the assumption of a strongly convex function. So 1/t in this case is not the lower bound. For strongly convex functions, the rate of convergence is actually exponential here. So 1/t is impressive, but not probably the best you can do. But anyway, we proved a similar thing without assuming strongly convex functions, but then we had to assume that the functions are smooth, which is not really what you want. So we had a hard time really publishing this, because the main idea for using proximal operator is that you don't have smooth functions. There's no point there. You assume that the functions are smooth. But anyway, everything holds with the smooth functions as well. And that is what we have also proved. Okay, so now related to the problem of constraints, you usually end up with a situation, and I make some. I will show you some examples. Right. Don't worry, it looks like very theoretic, but very soon we make some examples. You end up with a situation that your optimization is your constraint set is an intersection of a lot of different sets. Each set is usually simple to deal with, but when you take the intersection, it becomes difficult. A simple example is the polyhedral sets. If you have half spaces, a combination of them can give you very complicated sets. It can be very hard to find your solution. So the idea is that, you remember for non-smooth optimization, we had these proximal operators here, we have projections. So these projections are simpler to understand, they have some geometric meaning. Now you have some algorithm which is based on stochastic or randomly selecting both the terms in the objective function and the constraint. You randomly pick a constraint and then you project onto that. So you have this linear combination in the last line that makes sure that you can actually make a vanishing step size. And you do basically the same thing. You have two versions. Either you do proximal operator or gradient on the term that you choose, and then you project. Okay, so you go randomly and you hope that this converge. And then there is a theory explaining this also by Berserkas, but this is more recent. This is from 2016. So if you choose a very particular choice on step size, which is 1/² t for the objective terms, then you will converge in the order of 1/square root t, which is slow, but okay, that's the best we have. Again, everything is based on vanishing step size, so this is a problem, and this is the state of it. There's no variance reduction technique for this one. Okay, so now I basically covered what I wanted to say about the theory. I will go through some examples. This is basically the motivation for us to really learn about this large scale optimization, and basically it goes back to NLP application like this back in childhood. So the example that I'm going to show you is the classical clustering problem. It's an old problem. Nowadays you have different clustering modes. You have graph clustering, you have subspace clustering, you have different things to cluster. But now I'm talking about the original vector clustering, which is basically the problem that someone gives you a set of data points. You want to partition them into sets, where each set has elements which are close to each other, and the sets are far away from each other. Okay, so this is the classical clustering problem. The reason that we studied it is that we wanted to combine it with some other things that I will show later. But also from theoretical point of view, it has been recent. I'm going to talk about it. So a very famous optimization framework for solving this problem is that you consider partitions and some center is connected to the partition. So what you do is that you minimize the sum of the distances of every data point to its corresponding center. Okay? And you want to optimize this over the centroids and the partitions. Okay, now if you have this optimization and you do something alternatingly between the partitions and the centers, then you will get the so-called Lloyd iteration, which is the basis of the Kane example. If you fix the centroids, then the partition is nothing but assigning every point to the closest centroid. If you fix the centroids, if you fix the partition, the centroids would be the average of each partition. So you go on until you converge. The problem is that this is heavily dependent on your initialization. It's very sensitive. If you have worked with K-means, you know that it's very sensitive to initialization. There have been rich literature on different methods to deal with the initialization of K-means. But recently, people came up with something with theoretical guarantees as well, and that's what I like. Theory. So basically, the idea is that you do a kind of PCA before you apply K-means. You take the matrix of the data, you apply SVD, you get some subspaces spanned by the singular vectors, and then you project everything onto that. You get PCA basically, and then you apply a naive approximation algorithm for clustering. And there are standard approximation algorithms clustering, and after that you use this as an initialization of KSVD of SVD K-means, and that would converge. There's a theoretical guarantee for the convergence of this, and the theory, basically the theory is based on the proximity condition. So you pick a point, and that is, okay, now I have to show this to you. So this is the data point. These are two centroids, and this data point is assigned to this centroid. So you take a line between them, and then you project this point onto the line connecting them. You calculate this D1 and D2, and D2 should be much larger than D1. That is the condition. So you see that it makes sense. So if you start from such a case, and how larger depends on some constant which depends on the whole structure of the data. But if this holds for every data point, then you get a perfect recovery. Proven. Theoretically proven. Okay. So the problem with this scheme is that, first of all, it needs to solve an SVD. And if you have some thousands of data points, SVD is basically very difficult to do. And the other problem is that this is a general problem in K-means. You need to know the number of clusters beforehand. This is a classical problem in K-means. Another thing which is interesting for us, but maybe it's not so popular, is that if nowadays you might want to do machine learning based on classes. And that means that you want to use clustering as a regularization in other machine learning problems. K-means is difficult to be incorporated with other optimization techniques. Either you do them into sequential way, but you cannot come up with an easy joint framework to do clustering and your other machine learning tasks. So then people came up, based on this motivation, they came up with this convex framework for optimization. This is called the sum of norms clustering. So the idea is, actually we came up with this idea and then just search the literature and it worked. It's very difficult. So the idea here is very simple. Instead of assigning a centroid to a cluster, you assign to each point a centroid. So now each data point will have its own individual centroid, but now you add a convex term to promote equality between the centroids. So you make many of the centroids equal to each other. Okay? And that term is actually the sum of the L2 terms. So the sum of the L2 terms promotes a sparsity, and the sparsity in this case means that the centroids will be equal to each
So
other.
in the first iteration, the centroid corresponds to the point itself, or it's something different?
Now you don't have you don't have a clear distinction between partitions and the centroids. You don't have the partitions in your optimization, so you don't have this alternating method anymore. You have to solve this as a convex optimization problem.
Direct, with no alternating. And when you start, the centroid corresponds to the points that you have in the data.
Yeah,
I see. Mm-hmm.
Yes, but because this is a convex optimization, you don't care much about how you initialize it, because it's going to converge globally if you do a good job.
So it seems to me that you're kind of, so from a really like, I don't know even how to say, you're kind of going from you're framing this as if it's a sort of agglomerative clustering thing. So you're moving away from what really the advantage and the concept of variance is. Basically, starting from centroids that are much less than the number of data points that you have, and you're almost going like in the direction of what like a hierarchical clustering would do, right? So each point is being gonna.
Yeah.
Does it make sense?
Yes, absolutely. So exactly, that is the point. Another interesting observation about this optimization is that you have a hierarchical structure. So if you're familiar with the this type of L2 or sparse regularization terms, you know that you get a hierarchical structure with lambda. When you change the regularization parameter, you get different levels of sparsity. So there is a hierarchical structure here. And that is how it is framed. So I would say that this is a bridge between k-means type of optimization and hierarchical clustering. So I mentioned this cluster path algorithm. I really didn't want to talk about it much. I just wanted to say that it was slow. But now that you've read this issue, it's basically based on the issue of hierarchical clustering. So the technique is, from optimization point of view, is called the homotopy algorithm. So you change lambda and then you follow the solution, and it should be easier. But when you follow, basically what you do is that you are doing the hierarchical clustering. So this is an interesting thing with this optimization. But anyway, because you are dealing with a non-smooth optimization, this is really difficult to solve. Even if you apply cluster paths, following the path of the solution is difficult, really slow. And the other thing is that you will have a lot of terms in your objective function. So you see that now you sum over k and l, and if you have 100 points, that means 10,000 terms.
What is L?
Two different data points. So the summation is over every pair of centroids. That is really, really high. First of all, I mean, you can prune this, so you don't need everything to be connected to everything from the theoretical point of view.
Sorry. So the second sigma is like sigma over L, comma, sigma over K less than L?
Yes, K and L such that K minus L. You don't even need to have the K less than L, but you get repeated terms because it's symmetric. Okay. It's easier for theory. You don't see too many twos appearing. So this is about clustering. So surprisingly, when we found out this, we thought that somebody did the analysis. So it's typical that when you have a convex optimization, there's a standard way to find some conditions under which this works perfectly. You have the so-called planted models, and then you can show that it's okay. Surprisingly, it was not in the literature. So I'm not going to go through all the things, but we actually proved that if we proved the condition for perfect recovery of clusters through this process. So basically, it's based on the diameter of the clusters and the distance between the centers. So if the clusters are far away from each other and the diameters are small, basically this condition is satisfied. You see the capital D on the left-hand side, all these are distances, and right-hand side, and you have to choose the lambda in that range. So this is really good both for selecting lambda and for recovering the sets. So this is what
You would introduce this by saying this was applied for natural language processing? Just the whole framework setup?
Yeah.
What was the actual application?
I will show it in the next one. The application was mainly from NLP, and if you think about it, actually, this also comes from word-to-weight. So this is really how we end optimization. I will show you. Just to give you an answer, we wanted to have the idea of topic in word and myth. Okay. So you see that actually this is good for what I previously introduced as the incremental optimization. So you see that the objective in this case consists in many different terms, but it can be written in this additive form of individual terms by just breaking down this first term into many parts. And now you can apply the stochastic proximal algorithm. And it turns out that the proximal operator for this function is very easy to calculate. So we calculated it. There's a closed form relation. One good thing with this optimization is that each term only depends on 2 data. The whole thing is a large optimization, but each term only depends on CL and CA. So basically, for doing the incremental proximal algorithm, you have to only pick 2 points and do the proximal operator, and then you leave them and go to the other. So that leads to a very cheap iteration for incremental optimization. Okay, so the proximal operator in this case is very simple. You pick 2 points, you have 2 centroids, you move them toward their corresponding data points, and then what you do is that you do something that we call the symmetric shrinkage operator. So the difference between symmetric shrinkage operator and the conventional shrinkage operator is that for conventional shrinkage operator, you pick a point, you move it towards 0, and then if it is too close to 0, it will actually get absorbed to 0 and stay there at 0. For the symmetric shrinkage operator, you pick 2 points, they will be attracted to each other, and once they reach each other, they will stay. So now I have a video of this running on a small toy example. Okay, so this is your data set, and I'm just going to run the proximal incremental algorithm. So every time you're picking 2 points, and they're going to be attracted to each other. So you see that they're getting closer to each other, and they are getting clustered. These are the centroids. So in the end, you should end up with two centroids. But in this example, we have 2. They're going to get attracted to each other. But I chose a big step size in this case because otherwise I had to run it for hours. The actual algorithm completes in less than a second, but with say 1 million iterations. But if I want to make this video, it would be very so intentionally I made the step size very big so you get the variance. You don't see that it finally converges, just for better illustration.
Do the clusters have like a tangible downstream benefit in practice? You found a clustering, but the question is, do these topics or whatever, like, are they semantically coherent? Do they help in some kind of extrinsic task?
Yeah. So this is the part that we haven't done yet. We haven't now who's implementing this on the actual data. But since I will show you the optimization, and you will see that actually implementing that was a little bit tricky. So we are in the stage of really implementing right now.
So I have a follow-up question that I should have asked earlier, but it's sort of along the same direction of John's, but more general. I see nowhere in these formalizations, notion of the quality of the clusters, right? I mean, when you think about traditional k-means, then there is always some either information theoretical measure like purity, or a tool like silhouette score and so on that you would use to determine optimal parameter assignments of their step size and so on. All these some guiding tools that would tell you what's good and what's not. And here there is no notion of quality anywhere, of the solution. So how do you measure that?
So your question has two different answers. One is related to the application. The other one is related to theory. For application, yeah, what you said is correct. You need a metric for calculating. It's basically the same metric as previous, but somebody needs to run it on some data set and see that tune the parameters in order to get the best quality based on previous. But from the theoretical point of view, we had it. So this is exactly the quality. From theoretical point of view, you assume some underlying truths, and this is called the planted model. You assume that there's an underlying perfect case, and you're asking if your algorithm can recover this one ideally. And this is the condition. Basically, under this condition, you can recover everything perfectly. There is no sense of metric. You can have the analysis based on error, so you can extend this to an error analysis. So if this is not satisfied, I'm not going to get the perfect clusters. But how close I'm going to get to that? This is something that we haven't done. It turns out to be difficult to do the error analysis from theoretical point of view. But of course, we have in that paper we have some results on actual data set. I don't remember what case. We did some synthetic experiments, and some students have done that. So I'm not sure what experiments we have, but in the paper we have also some empirical observation. And exactly, it's the same as you said, based on some.
So in the video you showed the clusters algorithm stopped at 2 clusters, right?
Yes.
So what term in the equation stopped it further collapsing them 2 clusters into one?
In here, so this is related to the selection of lambda. If you look at this equation, basically you have 2 competing terms. One is that the argument here, which takes every point to the data, to the correct position of the data. So that would separate the points from each other. And then you have this operator which brings them closer to each other. And they fight with each other, and they will stop at some equilibrium. The equilibrium is defined by lambda, because you see that lambda is here. So that would control the equilibrium between them. If the equilibrium is in the direction of combining everything, then the 2 clusters start to combine, you will get 1 cluster. And if lambda is too small, then they will go closer to their data points, and the clusters will break down. So this condition basically reflects the same thing. So you have a range for lambda. Lambda should be larger than something and smaller than another thing to make sure that you're not losing it.
But the 2 Ds are something about the true underlying clustering that you actually can't know.
You can't know. So you cannot choose lambda based on this. So the actual use of this can be to select lambda. So if you knew the 2 Ds in this case, you could put it in this equation and then select the lambda easily. But because you don't know it, you should do the cross validation. So you have to play with lambda and see where you get the best metric. But usually, so this is a very popular discussion in this area. When you move from parameter the order selection, like the number of clusters, to something continuous like this lambda, you're not really solving the problem. You're just changing the problem to something different. But actually, in practice, you gain because this lambda is much easier. You usually have a range. If you have clear case, usually selecting that lambda is very simple.
So to be clear, then you do select the lambda, but you don't actually choose the number of clusters you're going to have.
Yeah.
When you actually run this.
When you run it, you have only 1 lambda. Yeah. Here you don't have any number of clusters. This n is the number of data. You only select lambda.
And then how do you get an intuition for what the lambda should be for a new set?
From theoretical point of view, lambda should be something related to geometry of
Yeah,
clusters.
from a practical point of view, if I have a new data set, it's a cluster. where do I start?
This is
Trial
the tricky
lambdas.
part.
Well, what's your first lambda?
You should so practically what you do. This is usually in any machine learning. You don't have a sense of lambda usually. You can get an upper bound certainly. So there is an upper bound where everything will be collided at one point. You can start from make the middle point and then you break it until you get there. So there is an upper bound for lambda. Right. But certainly when you start, you need to go through a stage where you check lambda by increasing it, and at some point you have to stop.
I mean, but I actually don't even know, like, what's the range? Like, it can be greater than 1.
Lambda can be anything positive.
Right, so.
But there is a number, there's a maximum. But there's a maximum number for lambda where all CKs will be equal to each other. That is basically, let me see if I can keep. That would be in the range of the radius of all the data.
Okay.
That's assuming that everything is a big cluster instead of treating them as a independent cluster. Then you have the radius of that big. Yeah. So you can start from that. If you start from that, you definitely get all CKs equal to each other. So in this experiment, for example, what I did was that I knew the range based on this theory. I had an idea. Of course, I knew the correct beat, but still, I knew a range, and I just fine-tuned it after I made a case. But this is the same for sparse modeling. So if you know about lasso many years ago, you had the same problem with selective lambda. It's still, I guess, it's not the problem is not completely settled. You have some information theoretic measures. You can have similar things here, but yeah, selecting the regularization parameter is. Okay, so now, because I don't have much time, this is the interesting part for me because this is what we propose. But I'm going to skip a big part of it, just mention some introductory thing. So you can now have the variance reduction schema on top of it. So we did just the proximal operator. But then this variance reduction is going to be, it's good in terms of convergence, but the problem is that you're losing a nice property of optimization. The property was that every time in each iteration, you pick 2 points, you make them close to each other. Now that you have variance reduction, because you are making a combination of all this table, you basically need to update every point. This is here in the red part. So this red part will be added from every data. This is the summation from every data point, and then you have to update x, which is the state of all data. So that is very dense, and when it actually updates all the data points, that is a problem. You're losing a very nice property of the previous, and that is the cheap iterations. Well, actually, we came up with a solution. The idea was that you only update those parameters that you are actually. You freeze the rest. Even if you are doing the variance reduction, you freeze the rest. It turns out that we have both theoretically and practically shown that this is going to converge the same as the previous one. But actually, I was preparing this a week ago, and then I went to one of the papers. I realized that actually this idea was there in some early work, but it was not mentioned later for some reason. It was called in that paper just-in-time parameter update. So we are doing basically this just-in-time parameter update for Saga. It turns out that, so this is the algorithm. I'm not going to go through it. Certainly, I'm not going to have enough time to do that. There are some corrections. You have to do some corrections to the algorithm to get it to converge. But basically, this is the same. So we have the original Saga versus the modified one, which freezes the parameters. It turns out that in the standard data system to try, there is no practical difference. The difference is that this is in terms of the number of iterations. This is actually, so our algorithm is actually in terms of real time, much faster because the iterations are cheaper. So basically, you should get a bias. If this one is not epoch, but the actual time, you will get a bias in here, which reflects the fastest iteration. Okay, so we could also theoretically prove that this is the same as sine. Okay, so I'm gonna just skip this part. So just to mention what we were trying to do. This is the formulation that we considered with. The idea was that we use the skip gram negative sampling thing, and then we add this condition to that. We have a student who will try to do that with smaller data sets, and we're trying to scale it. It's a little bit tricky. We have all the tools now, but now this is a non-convex optimization, so tuning the parameters is the problem right now. But now we have a non-convex version. Another application was with optimal transfer, but I'm going to just skip it. Okay, so this is the optimal transfer part. So then for optimal transport, we had this constraint version of variance reduction. So this is going to be submitted soon. Okay, so now I'm going to the second part of this talk. This is about something, and so the nature of this part is actually more preliminary because I have just started to learn more about this area. My intention was to do an analysis of deep learning from theoretical point of view, but then we found a nice way to explain and also modify everything that I'm going to just explain. But of course, everything has a kind of preliminary nature. So, okay, so the idea here is that I assume that you're familiar with deep learning. Everybody is. So you have iterations where you do a fine transform, or just call it linear for now. You have some linear transform, and then you do some nonlinearity on top. From the point of view of somebody like me with the optimization the optimization background, and this looks like an optimization step. So in a typical optimization step, like it's clear in the proximal. You will have a proximal operator and a gradient, and you apply them together. You will get something that's structurally similar to deep learning. So if I could say that this proximal operator is the same as nonlinearity, and the gradient is something that creates this linearity, then basically these two things look similar, or at least they're connected to each other. Right? So this is not only observed by me. There's a very nice paper now out. I got a copy of it. It's a very nice paper that tries to optimize the actual optimization people. That will do a similar thing. Now, of course, from the machine learning or computation point of view, this is not very surprising. So if you think about it, deep learning is nothing but a model for computation, right? A continuous value type of extension of old machine computation machine. So it's not surprising that optimization is trying to use this structure as a model for computation. So you see, it's not surprising that they are similar to each other. But anyway, people started to exploit this fact that they are similar to each other. From 2010, you can see some attempt. If this is the case, then you can remove the optimization algorithm and you put a deep neural network which learns the solution of an optimization. This is done for lasso optimization, and it's called LISA algorithm. I guess nowadays it's becoming more popular. It was proposed a long time ago, but now because it becomes very handy, people use it more. So yeah, deep learning can replace optimization, but just training a neural network which solve the optimization. But now the question I want to ask is that can optimization replace deep learning? If they are so similar to each other, maybe you can do something like optimization that will do the same thing as deep learning. The answer is no and maybe yes. So it's no because the deep learning, if you look at the one iteration of an optimization, what you see is that the difference between the two layers is very small. That is the idea of gradient descent. But in deep learning, the layers can have a lot of effect on the data. So you can say that, yes, they are similar to each other. You can replace it if you only talk about deep neural networks, which have an incremental effect on the data in each layer, and then you have a lot of layers. Then the similarity becomes more. Okay? So now we're talking about this kind of deep learning, where each layer will do a small job, but you have a lot of them to do the whole process. And incidentally, this is not also a new idea. You see the same idea in REST. Okay. So this is basically the idea. You add I assume that you're familiar also with residual networks. They're becoming very popular in applications. So what happens is that you will have these branches which will be added to your data. So this layer will become just a correction to your data. Instead of saying that this next layer is going to be only a function, now it's a correction to the previous. So usually what happens is that the effect of each layer is going to be incremental, and the number of layers that you need will be much more, 50, 60 layers instead of 3, 4. So actually you're not going to get the problem with vanishing gradient. When you do the deep learning, you know that when you go back, the gradient becomes either very big or very small. If you do then you have a scaling problem. This one doesn't have it, and there's a clear theoretical reason. So now we are taking this to the extreme, and we say that, okay, we want this layer to be very, very incremental. In that case, if you're familiar with, I suppose that all of you have some analysis. So if you have a structure which is very incremental and you have a lot of that, you get a differential equation. Right? So basically, the limit of this structure is a differential equation, and it has a geometric meaning. So basically, I just did the math. I started from a single layer, I made it very small, and then I took the limit, I got this differential. This is something that we call artificial nerve fiber. Now, why do I call it nerve fiber? It's because to keep the same relation with the biological system. So we know that one layer of deep neural network has a biological meaning as well. Also, this one can have some biological meaning. You have certain nerves, the actual neural cells, which are long enough so that you cannot relate the beginning and the end just by a timeless relation. So you need a wave equation to explain the change. And that needs an ordinary differential equation, and this is similar to this one. Usually in practice, people use linear differential equation, but this is artificial, so it can do. Okay, so the idea is that you start from a feature space, the trivial feature space, which is your data, and then you go on and through a path which creates your final feature space. And at each point, the change in the feature space should be inside the linear subspace defined by this equation. Okay? So this is a linear subspace because you can change this linearly and everything. So from the abstract point of view, you're having this problem that you have linear subspaces assigned to different points, and now you have a path going through this linear subspace. And this is a very well-known problem in control theory or in differential geometry. Okay, so just to step back and look at what we are doing, we have these deep neural networks, and we have this optimization algorithms, what we talked about. And now we introduce this ANF, which is something in between. It's from one point of view, it's a neural network. From one point of view, it's actually a local search algorithm. And we can actually benefit from this. Okay, so this is the crucial part, and I'm going to just introduce this slide and go very fast end of talk. You can have a different interpretation of this differential equation as a regularization. So the idea, you remember that now the idea is that you have subspaces assigned to different points in the space, and you have a path going through. Now you can have two situations for this subspace. So these are the subspaces. This is small lines with subspaces. Then you can have two situations. One is that they are a random line. One is they are well structured so that they form curves. Okay? This is called in differential geometry and control theory. This is called an integral distribution, and this is called a non-integral distribution. Okay? So the nice thing is that if you have an integral distribution, if you start from one of the points here, you will remain on this curve integrated from this subspace. So basically, if you are in this situation, then you have a conventional regularization, meaning that you're basically saying that the data should be on this curve. Okay? You're doing it in a roundabout way by introducing these subspaces, but basically that's what you're saying. You're having a machine learning technique which restricts everything to this curve. In general, that would be a manifold, not high dimensional. With this one, you don't have that property, and it turns out that there's an easy way to check that if you're in this situation or in that situation. This is called the Frobenius theorem. If you check that condition here, you see that you're actually in this situation. So basically, you are regularizing in a non-conventional way. Here you have these sets which regularize your data, but here you are regularizing through a different machinery, and we haven't understood it yet. But we call it a geometric regularization. This is about the introduction to this concept of artificial neural fiber. We'll not have time. We actually tried it on actual neural data. We have a project with the mice. You have from the brain, from the neural. Usually you get this fMRI data where everything kind of aggregated, but here we have a high resolution data from Apple. They're generated from the neural level, and then we can actually model it with this differential equation, which is artificial neural fiber form. And it turns out that this is actually a very good model. So it seems that there's a biological value to the differential equation. But yeah. The second part that I wanted to talk about is that we could use this structure to prove that deep learning can reach any function. This is not very popular nowadays because people are interested in the idea of generalization, and this is against generalization in a way. But some years ago, it was a hot topic, knowing that the deep structure could synthesize any function was an open problem. So we proved it with finite widths. And basically, the idea is that if something is of this form, it's not restricted to any set. It can go anywhere. So we introduced some converse form of the theorem. I'm just going to skip the part that talks about using this for machine learning. We actually use this structure on a simple data set, MNIST data set. It's very easy. Probably anything works with MNIST. Anything sophisticated enough work, but actually we tried it, and this one also worked. And this data set. This is old data. We have new one that even goes higher than this with basically batch normalization. And so you can add to this some normalization step that will help to us. And then we have also the backpropagation idea here, which is actually called the parallel transport. So you calculate the gradient at the end of the path, and then you backpropagate it from parallel transport. The good thing is that you don't need to keep all the path to do the parallel transport because of these properties. So the nice thing is that you have much less memory for doing. You don't need to keep the whole path, the whole feature space. You just we have a new student who's going to implement this. Haven't done it. Convolutional neural. And with this, I'm going to just conclude. There are some directions for future work. I've talked about many of them already. One thing is that variance reduction techniques they are not actually studied very well in the context of non-convex and primordial algebra. There is a paper in this year's NIPS for primordial optimization. There are some old papers about non-convex algebra. Even deep learning hasn't tried variance reduction, but the gain was so small that nobody. And then the other thing is that you can add a statistical flavor to all of this analysis. And this is what I'm doing right now. I talked about this application to NLP, and hopefully we get the results at some point. Adversarial learning is something which is a natural match to this process. You can have two paths fighting with each other, and you get something in the form of a game theory. Other topics of interest for me, network sciences. I didn't talk about it. Now I knew about optimization. I knew about all this stuff. Doing, for example, community detection with these things. I just learned about message passing. I mean, I knew about message passing a long time ago in the context of image processing, but it turned out that this is a strong tool to do community detection. I don't know if you knew about it, but this was new to me. So we have had a lot of fun with this message passing and context detection. Now we are submitting a paper to physical review conference. We have a student from physical department who's developed this message passing algorithm for multi-layer network, which is very interesting. And also the other thing is that all of this that I talked is kind of related more theoretically to the question of fastest optimization. So this artificial neural fiber is going to model the optimization. So if you optimize it, that means that you're optimizing your optimization. So this is a new look at everything, but it's also introduced Michael Jordan has papers on related topics. So with this, I want to conclude and be happy to hear about your comments and questions.
So in that last part, we current faster than equivalent amount of.
It is faster. So here you can see the result. This is something that is called media. You get so it's done on my own computer. You need something like 30 minutes to get the result. This is less than a minute reaching here. So because you don't do back propagation, what you lose is that you don't get 99, you get 98. Yeah, you're working on it, but certainly you gain something.
Anything else? Thank you.